high above the familiar blue of oceans and air, beyond the thin breadth of atmosphere where weather fades into stillness, space is not empty. It is laced with invisible threads, long, sinuous lines stretching from star to star, from galaxy to galaxy, weaving a hidden lattice that holds shape in the silence. These are cosmic, magnetic fields, unseen, intangible, yet everywhere, binding the universe in ways most eyes will never notice. On Earth, magnetism is a quiet servant, guiding compasses, shaping the auroras, whispering to iron in the crust. But here, in the vastness, it becomes something else entirely, an ancient architect, tracing patterns across space-time itself. They coil through interstellar clouds, gently steering rivers of dust into the seeds of new stars. They wrap around planets and suns, sculpt the long tails of comets, and curve the jets of plasma that erupt from the hearts of galaxies, launching them millions of light-years into the void. Even the journey of high-energy particles, messengers from distant supernova, is bent by their unseen grip. And yet, for all their power, their origin is a question left unanswered. Did these magnetic fields awaken in the first heartbeat, after the Big Bang etched into space before the first light? Or did they rise more slowly, drawn from chaos by the subtle motions of matter and energy over cosmic time? To uncover the magnetic skeleton of the sky is to strip away the visible and find the hidden framework beneath, the delicate but unyielding lines upon which cosmic history has been written. Somewhere in these lines lies a story older than light itself, and perhaps the key to how the universe became what it is. The story of the magnetic skeleton begins not in the cold reaches of interstellar space, but in the warm and familiar landscapes of Earth, long before anyone knew of galaxies or the curvature of space-time. Humanity's first encounters with magnetism came in the form of small, unassuming stones, loads. Ancient mariners discovered that these naturally magnetized minerals could align themselves to the north, as if in quiet conversation with some hidden force. The compass was born, and with it the first sense that the earth itself was enveloped in an invisible field. For centuries, magnetism was regarded as a curiosity, a navigational tool, a quirk of certain metals. But in the 19th century, a deeper understanding began to take shape. Michael Faraday revealed that electricity and magnetism were not separate phenomena, but different faces of the same fundamental interaction. James Clerk Maxwell distilled this insight into a set of equations that described how electric and magnetic fields could travel through space together as waves of light. The realization was profound. Magnetism was not confined to rocks and iron. It was part of the same force that painted the world with sunlight. The first hints that magnetic fields might exist beyond Earth came from our nearest star. The Sun, studied through telescopes in the 17th and 18th centuries, revealed mysterious dark blemishes, like sunspots. By the early 20th century, astronomers discovered these were regions of intense magnetic activity, thousands of times stronger than Earth's field. Sunspots rose and fell in an 11-year cycle, a rhythm driven by the twisting and tangling of the Sun's magnetic lines beneath its roiling surface. The Sun's corona, a halo of hot plasma visible during eclipses, was found to be sculpted by magnetic loops arching far above its surface. In early solar photography, these loops appeared like delicate brushstrokes of light, tracing the magnetic scaffolding that held the Sun's outer atmosphere in place. The mid-20th century brought a leap in vision. Radio astronomy opened a new window on the cosmos, revealing phenomena invisible to optical telescopes. Astronomers detected synchrotron radiation, a special kind of radio emission produced when high-energy electrons spiral around magnetic field lines at near light speeds. This was the first unambiguous proof that magnetic fields permeated not only the Sun, but the space between stars. Polarization studies deepened the picture. Light waves, vibrating in specific orientations, hinted at alignment caused by interstellar dust grains, themselves rotated and ordered by magnetic fields. In this way, the fields left their fingerprints on starlight, revealing patterns that stretched across whole regions of the Milky Way. Theoretical work began to catch up. Subramanian, Chandrasekhar, and Enrico Fermi explored how magnetic fields could arise in the tenuous gas between stars, how they might grow through turbulence and motion, and how they could influence the birth of stars themselves. It became clear that magnetism was not a background detail, but a dynamic force shaping cosmic evolution. Detection methods refined over time. Using arrays of radio dishes and more sensitive receivers, astronomers traced magnetic fields across the Milky Way's spiral arms, mapping lines tens of thousands of light-years long. Similar structures were found in nearby galaxies, coherent fields ordered on galactic scales, threading through disks of stars and gas. By the 1970s and 80s, it was no longer a question of whether magnetic fields existed in space, but how far their reach extended. In galaxy clusters, vast collections of hundreds or thousands of galaxies, astronomers discovered giant lobes of radio emission, inflated by jets from supermassive black holes and structured by magnetic forces. These fields extended for millions of light-years, coherent over scales so large they defied easy explanation. Even the space between galaxies, once thought to be nearly empty, was found to contain a thin plasma, the intergalactic medium threaded with magnetic fields. Though weak, these fields still shaped the motion of charged particles drifting between the great cosmic structures. The implications were staggering. If magnetism could span these distances, it could not be an incidental feature of certain objects. It must be a fundamental component of the universe's architecture, woven into the same fabric as matter, energy, and gravity. Yet the more magnetic fields were observed, the deeper the mystery became. Unlike planets or stars, whose origins could be traced to the collapse of matter under gravity, the birth of magnetic fields was elusive. Observations showed them everywhere in ancient galaxies, in newly formed systems, but the mechanism by which they first emerged was unknown. The magnetic skeleton of the sky was no longer a poetic image. It was an observational reality, but humanity's first view of it was incomplete. Each detection was a fragment, a stretch of lines in one galaxy, a bubble of magnetized plasma around a black hole, a ribbon of polarized dust cutting across the Milky Way. It would take decades of surveys, new generations of telescopes, and the accumulation of millions of data points before a more coherent picture began to emerge. Slowly, the outlines of the skeleton became visible, a network of ordered fields within galaxies, tangled turbulence in the regions between them, and the faint suggestion of threads extending across the great cosmic web itself. Yet in these first discoveries lay the seeds of an even greater shock. For if magnetism is this widespread, if it is as ancient and large-scale as the early findings hinted, then its origin story might reach back to the earliest moments of time, to the first fractions of a second after the Big Bang. That possibility would force scientists to reconsider the role of magnetism entirely, not as a secondary phenomenon, shaped by cosmic evolution, but as a primary force that may have helped shape evolution itself. The next chapter of the story would push this realization to its breaking point. Observations would reveal magnetic fields in places and epochs where they should not yet exist, and the skeleton of the sky would no longer be a quiet presence in the background, but a direct challenge to our understanding of how the universe came to be. The first maps of cosmic magnetism were fragments, scattered, partial, incomplete. But as the data deepened, a startling pattern emerged. Magnetic fields were not rare curiosities. They were everywhere, everywhere the instruments could reach. In planets and stars, in the swirling disks of galaxies, in the vast reaches between them, the invisible threads were there. And they were not faint, fading traces. In many places, they were strong, structured, coherent over distances so vast that the mind strained to grasp them in the Milky Way. Radio maps revealed spiral arms not only traced by stars and dust, but by magnetic lines tens of thousands of light-years long. These fields were not chaotic. They had direction, structure, and a strength comparable to that of the sun's field, spread over volumes a trillion times larger. Nearby galaxies told the same story. Polarized light from their disks and halos showed magnetic lines arcing gracefully, from core to edge, threading through regions of gas and dust, bending to the galactic rotation. Some even wrapped into ordered patterns along spiral arms, as if woven into the galaxy's very design. And then came the galaxy clusters, sprawling cities of hundreds or thousands of galaxies, bathed in hot, X-ray-emitting gas. Here too, magnetic fields appeared, stretching across millions of light-years. They were vast, ancient, and improbably organized in a universe governed by turbulence and chaos. The sheer scale posed a riddle. Magnetic fields require currents moving, charges to be sustained. On small scales, planets generate them through the motion of molten cores. Stars create them through the churning of conductive plasma. But on the scale of galaxies and clusters, the sources were harder to define. How could such immense and coherent fields arise, and how could they persist for billions of years? More troubling still, their origin seemed to defy the known timelines of cosmic evolution. Dynamo theory, the leading explanation for magnetic field amplification, can take a weak seed field and grow it over cosmic time through turbulence and rotation. But the young galaxies astronomers were observing, just a few billion years after the Big Bang, already had strong, ordered fields. The seeds must have been planted earlier, perhaps unimaginably early. The implications deepened with the study of cosmic rays. These high-energy particles, launched from supernova, pulsars, and active galactic nuclei, do not travel in straight lines. They are deflected by magnetic fields, their paths twisted into spirals, their arrival directions scrambled. This meant that the fields were not just large, they were powerful enough to influence particles moving at nearly the speed of light. The deflection of cosmic rays has a double edge. It hides their true sources, blurring the astronomical maps of their origins, but it also reveals the reach and strength of the fields they encounter, turning each cosmic ray into a tiny probe of the invisible structure of space. Perhaps most surprising of all was the role of magnetic fields in star formation. For decades, gravity was assumed to be the sole sculptor of collapsing clouds of gas and dust. But as instruments grew sensitive enough to trace magnetic lines within these clouds, a new picture emerged. Magnetic pressure often resisted collapse, slowing the formation of new stars. In some cases, fields guided the collapse along certain directions, shaping the birthplaces of stars into filaments and pillars. This was no passive background. Magnetism was an active force in the creation of light itself. Then came one of the most staggering findings: galaxy clusters. The largest gravitationally bound structures in the universe did not just have patchy, tangled fields. They had coherent magnetic structures stretching across millions of light years, a level of order that should have been impossible in such turbulent environments. These were not short-lived flukes. The evidence suggested they had persisted. For billions of years, the shock was as much philosophical as scientific. For centuries, gravity had been the architect of the cosmos in the human imagination. The force that assembled galaxies, governed planetary orbits, and curved the very fabric of space-time. Magnetism, by contrast, was a local player, a specialist. Force acting in stars, planets, and laboratory coils of wire. Now, observations were telling a different story. Magnetism was not merely an occasional sculpture of matter. It was woven into the scaffolding of the universe. It had shaped, and continued to shape, the largest structures in existence. But the deeper the evidence ran, the stranger the origin. Story became: no known process in the present-day universe could create the seed fields strong enough to explain what was seen. Stellar winds and supernova could contribute, but only after the first stars had formed, far too late to explain the magnetic order in young galaxies. Galactic dynamos could amplify fields, but only if something started them. The mystery of these primordial seeds began to point back toward the early universe. Two epochs that were not only distant in time, but exotic in physics: inflation, cosmic, phase transitions, or even processes tied to the separation of matter and antimatter. If true, that would mean magnetism is not an afterthought of cosmic history, but one of its original lines of code, written into space itself before galaxies, stars, or planets existed. This possibility reframed everything. If magnetic fields were born in the early universe, they might carry signatures of conditions otherwise invisible, imprints of forces, particles, or symmetries that no longer exist. They could, in principle, be fossils of physics from before the cosmic microwave background, before the first light could travel freely through space. In that sense, to understand the magnetic skeleton of the sky was not only to map the present, but to glimpse the prehistory of the universe, a past so ancient it lies beyond all direct observation, yet still traced in the invisible lines threading the cosmos. The stage was set for a deeper investigation, one that would require mapping the sky in radio polarization, measuring the twists in light from distant pulsars, and tracing synchrotron emission across the largest known structures. The goal was no longer simply to detect cosmic magnetic fields. It was to understand them as a coherent system, a hidden framework upon which matter itself had gathered and evolved. What had begun as a curiosity, a side effect in star spots and auroras, had become a challenge to the very narrative of cosmic history. The magnetic skeleton of the sky was no longer hidden in the background. It was standing in full view, and its presence was rewriting the story of how the universe came to be. Once the shock settled, the search deepened. If cosmic magnetic fields were everywhere, ancient, vast, and powerful, then the task was no longer to prove they existed, but to reveal their shapes, strengths, and origins with precision. The question became not if the skeleton of the sky was real, but how it was built. The Milky Way offered the first great laboratory. Here, Magnetic fields could be traced in exquisite detail, not just as distant features, but as structures winding through the very space we inhabit. Using polarized radio emission, astronomers mapped the galaxy's field line by line. The technique relied on the way synchrotron radiation emitted by electrons spiraling along magnetic lines is naturally polarized. As these waves pass through regions of ionized gas, their polarization rotated, a phenomenon called Faraday rotation. By measuring how the angle of polarization changed with wavelength, scientists could infer both the strength and the direction of the magnetic field along the line of sight. Over decades, these measurements revealed a surprising picture. The Milky Way's magnetic field is not random, but organized, with coherent spiral patterns following the galaxy's arms. Reversals in direction between regions and large-scale arcs stretching high above the galactic plane. The launch of the Planck satellite in 2009 brought a leap forward. By measuring the polarized glow of interstellar dust, Planck traced the fine filaments of magnetic fields across the entire sky. The results showed that dust grains tend to align with their long axes perpendicular to the magnetic field, effectively acting as millions of tiny compass needles scattered through space. The patterns they traced revealed a sky threaded with delicate, curving filaments, structures invisible to ordinary light, but unmistakable in polarized emission. These maps became a global reference, showing that the galaxy's magnetic field is intertwined with the structure of interstellar clouds, shaping how gas flows and how stars form. While Planck mapped the wide view, ground-based radio arrays provided zoomed-in detail. Telescopes like Meerkat in South Africa and the Very Large Array, VLA, in New Mexico targeted the galactic center, a region of intense gravity, turbulence, and star formation. Here, they revealed something extraordinary. Long, narrow, magnetic filaments, some tens of light years long, stretching vertically away from the plane of the galaxy. These filaments, discovered decades ago but now mapped in greater detail, appear to be rigid structures, resisting the swirling chaos of the region. Their origin is still uncertain. They may trace shock fronts, shear flows, or the boundaries of vast magnetic bubbles inflated by past activity from the supermassive black hole at the Milky Way's core. The investigation did not stop at the Milky Way's edge. In the lobes of active galaxies, where supermassive black holes launch jets of plasma at near-light speeds, magnetic fields were found to shape and confine enormous outflows. Radio observations revealed intricate polarization patterns, tracing ordered fields tens or even hundreds of thousands of light years in scale. Some of the clearest examples come from giant radio galaxies, whose lobes span millions of light years. In these colossal structures, magnetic lines appear to thread through the hot plasma like the grain in wood, guiding its expansion and preserving coherence over unimaginable distances. Perhaps the most ambitious step was to look for magnetism, not just in galaxies, but in the cosmic web, the vast network of filaments and voids connecting galaxy clusters across the universe. This search pushed the limits of current technology. The fields in intergalactic space are faint, perhaps 1 billion times weaker than Earth's field, yet they still influence the motion of charged particles and may play a role in galaxy formation. Hints of these fields emerged through studies of Faraday rotation in light from distant quasars, when their signals pass through magnetized plasma in intergalactic filaments. The rotation accumulates, leaving a small but measurable signature. Cross-matching these signals with maps of large-scale structure has begun to reveal where magnetic fields thread the spaces between galaxies, in 2020, the LOFA radio array in Europe produced some of the most detailed maps yet of this intergalactic magnetism, showing polarized emission from regions coinciding with the cosmic web, evidence that these fields are not confined to galaxies but are truly universal. Another powerful tool in this investigation comes from pulsars, rapidly rotating neutron stars that emit beams of radio waves like cosmic lighthouses. Because their pulses are incredibly regular, any delay or polarization change caused by magnetic fields along their path can be measured with precision by observing hundreds of pulsars scattered across the galaxy. Astronomers can reconstruct the three-dimensional structure of the Milky Way's field. This method has revealed not only large-scale order, but also small-scale turbulence, the tangled, chaotic component of the field that stirs interstellar gas. To understand how magnetic fields evolve, astronomers also study galaxy mergers. When two galaxies collide, their magnetic fields are stirred into turbulence, amplified by compression and shear. Observations of merging systems show chaotic polarization patterns, slowly settling into new order over hundreds of millions of years. These events offer a living laboratory for processes that may have amplified seed fields in the early universe. They also hint that magnetism may influence how merger-driven starbursts proceed, affecting the rate at which new stars are born. Piece by piece, the data has grown into a layered portrait: the Milky Way's ordered spirals and turbulent tangles, the dust-traced filaments of the interstellar medium, the vertical magnetic strands near the galactic center, the colossal, magnetized lobes of active galaxies, the faint but pervasive fields in the cosmic web. What emerges is a view of magnetism as a multi-scale phenomenon, from the microphysics of charged particles to the grand architecture of the universe. And yet, the more clearly the skeleton of the sky is mapped, the deeper its mystery becomes. Even the faintest intergalactic fields may be older than the first galaxies, perhaps dating back to the early universe itself. If these fields truly predate cosmic structure, then they are not just shaped by the universe, they may have helped shape it. This would elevate them from background actors to foundational forces, standing alongside gravity and radiation in the opening moments of cosmic history. The current maps are only the beginning. The upcoming Square Kilometre Array, SKA, when completed, will increase sensitivity to magnetic fields by orders of magnitude, enabling detailed mapping of both galactic and intergalactic magnetism across cosmic time. Combined with CMB polarization experiments and ever-growing pulsar catalogs, these tools will test whether the cosmic magnetic web is primordial or built later by astrophysical processes. The investigation is no longer confined to observing what is there now. It has become an attempt to reconstruct the universe's magnetic history, to trace the lines back to their first appearance, and understand how they have endured for billions of years. The deeper the maps became, the more the magnetic skeleton of the sky seemed to defy the universe's own timelines. In young galaxies, already strong and ordered fields appeared far too early for known processes to explain. According to dynamo theory, weak seed fields can be amplified by turbulence, rotation, and the motions of charged gas. But this takes time, billions of years, for the most coherent structures to emerge. The observations said otherwise. Galaxies only a few 100 million years old, mere infants on the cosmic stage, already bore magnetic fields, not just detectable, but mature. The seed field problem. This was the seed field problem. If the amplification process was too slow to produce these early strengths, then the seeds themselves must have been far stronger than expected. And where could such strong seeds come from? The present-day universe offers no known mechanism to create them. Magnetic fields generated by stars, supernova, or jets from black holes could only appear after those objects existed, long after the universe's birth. This left one possibility both thrilling and unsettling. The seeds were older than the first stars, older than galaxies, older even than the first atoms. They might have been born in the very earliest moments after the Big Bang. Primordial origins, if this was true. Then cosmic magnetism was not a byproduct of structure formation. It was part of the initial conditions. Several scenarios emerged. Perhaps magnetic fields arose during inflation. The universe's rapid expansion in its first fractions of a second, when quantum fluctuations were stretched to cosmic scales. Or maybe they were forged in cosmic phase transitions, moments when fundamental forces shifted their relationships, such as the separation of electromagnetism and the weak nuclear force. In these scenarios, magnetism could be as old as space-time, itself an original imprint from a time when the physics of the universe was utterly alien to the one we know. Magnetism in the voids of evidence in support of such ancient origins came from an unlikely place, the voids. These are the great empty expanses between the filaments of the cosmic web, places where few galaxies dwell and the density of matter is incredibly low. Yet even here, faint magnetic fields may persist. By studying the gamma rays from distant blazars, active galaxies with jets aimed toward Earth, astronomers discovered that their high-energy photons sometimes transformed into electron-positron pairs when interacting with background light. These pairs, deflected by intergalactic magnetic fields, could scatter gamma rays into delayed cascades. The patterns of these cascades suggested that even the emptiest regions of space are permeated by weak but coherent magnetic fields, perhaps left over from a time before galaxies existed. Magnetic influence on cosmic structure. If such primordial magnetism exists, its role in shaping the large-scale structure of the universe could be profound. Even a weak field, if present during the formation of the first stars and galaxies, could influence how matter flowed, cooled, and collapsed. It might help explain why galaxies formed where they did, why filaments took the shapes they have, and even why some regions of the universe seem to have more or less structure than average. In this way, the magnetic skeleton might not only trace the cosmic web, it might have helped build it. Violence in the magnetic lines. Magnetic fields are not static. In many astrophysical environments, they store energy in twisted and sheared configurations, waiting for a moment of release. When oppositely directed lines are forced together, they can undergo magnetic reconnection, a sudden rearrangement that releases colossal amounts of energy. This process is familiar in the solar system, where it powers solar flares and coronal mass ejections. But in the broader universe, reconnection may occur on scales that dwarf anything in our planetary neighborhood. In the jets of quasars, in the magnetospheres of neutron stars, in the tangled fields of colliding galaxy clusters, reconnection could unleash bursts of radiation, accelerate particles to extreme energies, and reshape the surrounding plasma. If cosmic magnetism is primordial, then such events might be modern echoes of processes that were shaping the universe long before the first galaxies formed. Active or passive architect? A deeper question began to surface. Is the cosmic magnetic web merely a passive outcome of cosmic evolution, shaped by matter, stretched by expansion, amplified by turbulence? Or Is it an active agent, influencing the evolution of matter itself? From the earliest times, if the latter is true, then magnetism must be placed alongside gravity, radiation, and dark energy as one of the great shapers of the universe. Its invisible lines may have guided matter into the patterns we now call galaxies and clusters. The uncertainty of the future, for now, the evidence is incomplete. Observations hint at primordial fields, but do not yet confirm them. Measurements of void magnetism could still be explained by more local processes. The alignment of magnetic structures with the cosmic web could be a product of later amplification rather than an ancient blueprint. But the possibility remains that cosmic magnetism is not just ancient, it is as fundamental as the fabric it threads through. If confirmed, this would make magnetic fields not an accessory to cosmic history, but one of its primary authors. The stakes of the mystery solving. This mystery would not only answer how the universe came to have the structure we see, it would open a window into physics beyond the standard model. Primordial magnetism could reveal properties of the early universe otherwise hidden from view. It might encode signatures of forces that no longer exist, or particles that have yet to be detected. It could even carry imprints from epochs before the Big Bang, if such eras existed. The skeleton of the sky may be the oldest surviving relic of the universe's creation, older than light, older than atoms, older than time as we understand it. Toward the theories, the escalation of the mystery demands more than observation alone. It requires a confrontation with theory, a journey into the realm of models that stretch the known laws of physics to their limits. From inflationary magnetogenesis to exotic particle couplings, from turbulent dynamos to the possibility of fields predating our universe entirely. The next step is to explore how science is trying to explain the invisible architecture revealed by the maps. The road ahead will lead into speculation, but speculation grounded in equations, in simulations, in the hard boundaries set by what has already been measured. The magnetic skeleton of the sky has emerged from the shadows. The question now is not whether it is there, but how it came to be, and whether it has been with us from the very first instant of creation. The evidence is laid out like the bones of some great, invisible creature. Magnetic fields in galaxies and clusters, threading the cosmic web, whisper of origins more ancient than stars. But to explain their birth, science must venture beyond what is directly seen into realms where equations are maps to places human eyes have never traveled. One possibility is that cosmic magnetic fields were born in the first instance of the universe. During inflation, the incomprehensibly rapid expansion that, in less than a trillionth of a second, stretched the fabric of space-time itself, tiny quantum fluctuations were magnified to cosmic scales. If the electromagnetic field was active during this period, those fluctuations could have seeded magnetic fields spanning the universe. Their wavelengths stretched beyond galaxies, beyond clusters, into the largest structures we can observe today. Another idea looks to cosmic phase transitions, moments when the universe cooled enough for its fundamental forces to separate and take the forms we know now. In the earliest moments, electromagnetism and the weak nuclear force were united in a single electroweak force. As the universe expanded and cooled, they split. This separation could have created violent outflows of charged particles, generating strong magnetic disturbances, ripples frozen into the plasma, preserved as the first magnetic fields. A third scenario ties magnetism to baryogenesis, the process that created the imbalance between matter and antimatter. If exotic interactions between particles occurred during this asymmetry, they might have twisted magnetic fields into being as a kind of byproduct of the matter-dominated universe we inhabit today. In all of these models, magnetic fields would be as old as spacetime's first moments, fossils of physics beyond our current reach, still etched across the sky in lines we cannot see directly, but whose influence we can measure. Other scientists propose that the universe began without significant magnetism, that the fields we see today are the result of processes within the first generations of stars and galaxies. One possibility is that massive stars, in their violent deaths as supernova, expelled magnetized plasma into the surrounding interstellar medium. These outflows, repeated billions of times across countless galaxies, could seed the cosmos with weak magnetic fields. Similarly, stellar winds from the first stars, huge flows of ionized gas, could have carried magnetic fields into interstellar space. Over time, as these winds overlapped and merged, they could have laid the groundwork for larger-scale fields. Jets from the first black holes offer another pathway. In the early universe, the collapse of massive stars may have produced black holes that launched powerful, magnetized jets into the surrounding gas. These could have seeded the magnetic skeleton far beyond their host galaxies, influencing matter on intergalactic scales. In this view, the early universe was magnetically quiet, and magnetism emerged gradually, a product of stellar evolution, galactic activity, and the slow work of time. Whichever seed fields existed, they could not remain as faint traces. They needed to grow, and here enters the galactic dynamo. This process relies on the motions of charged gas within galaxies. As the galaxy rotates, its gas clouds and stars move through spiral arms, generating turbulence. Conductive plasma, stirred by this motion, can amplify existing magnetic fields, winding them into coherent structures. The dynamo is powerful, but it is not fast. It can explain the fields in mature galaxies, but only if the seeds were already in place, whether planted in the first stars or in the first moments after the Big Bang. Beyond the dynamo, the physics of magnetohydrodynamics, the interaction between magnetic fields and conductive fluids, offers ways for fields to grow on smaller scales. In turbulent gas, eddies can stretch and twist magnetic lines, increasing their strength. These small-scale processes may not produce the vast coherent fields of entire galaxies, but they can feed the larger structures, supplying energy and complexity to the skeleton of the sky. Some theories go further, venturing into the territory of the extraordinary magnetic fields might couple to hypothetical particles like ixions, whose existence has been proposed to solve deep problems in particle physics. If such particles exist, they could influence how magnetic fields evolved, leaving signatures that could be detected in precise polarization measurements of light from distant quasars or the cosmic microwave background. Another speculation is that magnetic fields might be relics from a pre-Big Bang era. If the universe is cyclical, passing through endless expansions and contractions, then magnetism might survive each transition, carrying forward imprints of a past cosmos into the present one. Some have even wondered if magnetism could play a role in the mysterious behavior of dark matter. While dark matter is thought to be electrically neutral, there are models in which a small fraction could interact with magnetic fields, subtly altering the structure of galaxies over billions of years. One unifying theme in all of these models is the recognition that magnetic fields are not passive decorations. Whether they arose from primordial physics or astrophysical processes, They shape the cosmos in tangible ways, guiding the flow of gas into stars and planets, sculpting the jets of black holes into million light-year beacons, influencing the distribution of cosmic rays and the chemistry of interstellar clouds, potentially affecting the very architecture of the cosmic web. If they are primordial, then they may have influenced the formation of the first stars, perhaps even the emergence of galaxies themselves. Despite these theories, a definitive answer remains elusive, because magnetic fields are not directly visible. They must be inferred from the behavior of matter and light interacting with them: synchrotron radiation, Faraday rotation, polarized dust emission. Even with the most powerful telescopes, it is difficult to separate the contributions of primordial fields from those generated later. Cosmic expansion has stretched and diluted any original fields, while countless astrophysical processes have tangled, amplified, and overlaid them. Simulations attempt to bridge the gap, combining magneto with cosmological models to test whether observed structures could arise from different initial conditions. But the parameter space is vast, and many scenarios remain consistent with current data. Among the most radical suggestions is that the magnetic skeleton is older than the universe we inhabit, not in the sense of physical time within our cosmos, but as a relic from physics beyond our observable horizon. If the universe emerged from a quantum fluctuation in a larger multiverse, magnetic fields could have been part of the environment from which it was born. Their lines stretched into our space like the threads of an older tapestry. This idea is speculative, but it reflects the depth of the mystery. The magnetic skeleton might be the only surviving clue to conditions we can never directly observe, conditions that shaped not only our universe, but possibly countless others. The theories are many, but the deciding evidence will come from observation. If the faint fields in cosmic voids can be measured precisely, they could confirm or rule out primordial origins. If polarization patterns in the cosmic microwave background reveal signatures of inflationary magnetism, they could push the birth of magnetic fields back to the first instance. If no such patterns appear, astrophysical origins will gain ground. The coming decades will see this debate sharpen, as instruments like the Square Kilometre Array, Light by ARD, and next-generation cosmic ray observatories probe the skeleton in unprecedented detail. The stage is set for the next act, the transition from theoretical speculation to experimental test. The next chapter will turn to the tools themselves: the immense radio arrays, the X-ray telescopes, the pulsar timing networks, and the particle detectors that together form humanity's own skeleton of discovery, reaching into the invisible architecture of the sky. To study something that cannot be seen, something that passes through eyes and cameras without leaving a trace, requires tools of extraordinary subtlety. The magnetic skeleton of the sky is not drawn in light, but in the way light twists, fades, and changes as it moves through space. To uncover it, scientists must use the universe itself as both subject and instrument, turning photons, particles, and plasma into messengers. The front line of this investigation lies in the great fields of radio antennas spread across Earth. Arrays like Elofar in Europe, Meerkat in South Africa, and the Very Large Array in New Mexico work together to detect faint radio signals from distant galaxies, pulsars, and cosmic jets. Radio waves are crucial because many magnetic field signatures appear only at these wavelengths. When high-energy electrons spiral along magnetic lines, they emit synchrotron radiation, which is naturally polarized. The degree and direction of this polarization carry direct information about the field's structure. These arrays also measure Faraday rotation, the slow twisting of a polarized radio wave's orientation as it travels through a magnetized plasma, by comparing the amount of rotation at different wavelengths. Astronomers can calculate the strength and direction of the magnetic field. Along the wave's path, the coming decade will bring a revolution in this field. The Square Kilometre Array, a vast network of thousands of antennas across Africa and Australia, forming the largest radio telescope ever built. With unprecedented sensitivity, the SKA will map magnetic fields across millions of galaxies, chart the faint magnetism in cosmic voids, and measure the polarized light of millions of distant radio sources. Its resolution will allow scientists to detect the skeleton of the sky on scales from the interstellar filaments within the Milky Way to the vast arcs connecting galaxy clusters. For the first time, the magnetic web may be mapped in its entirety, where galaxy clusters collide or jets from black holes plow into surrounding gas. The plasma glows in extras. Telescopes like Chandra, XMM Newton, and the upcoming Athena mission reveal the hot, magnetized environments where magnetic fields shape the motion of matter on colossal scales. X-ray observations can detect shocks and turbulence, regions where magnetic fields are amplified, twisted, or broken. They also show how these fields confine hot gas, preventing it from cooling and collapsing into new stars. In combination with radio data, X-ray maps allow scientists to connect the magnetic lines to the matter they control, linking the invisible skeleton to the visible body of the universe. The cosmic microwave. Background CMB, the afterglow of the Big Bang, is an ancient canvas that might hold the fingerprints of primordial magnetism. If magnetic fields existed during the CMB's formation, they could have subtly polarized its light, or left small-scale temperature fluctuations in its smooth glow. Experiments like Light Bayard and CMB's 4 are designed to detect polarization patterns with exquisite sensitivity. By searching for specific modes of polarization, scientists hope to identify whether magnetism existed in the early universe, and if so, how strong it was. This is one of the most direct paths to testing the idea of inflationary magnetogenesis, the birth of cosmic fields in the first instant of time, pulsars, neutron stars that emit regular pulses of radio. Waves act as precision beacons. As their signals cross the galaxy, they are slowed, scattered, and rotated by the magnetic fields in interstellar space. By observing many pulsars in different directions, astronomers can construct a three-dimensional map of the Milky Way's magnetic field. This approach has revealed not only the large-scale spiral structure of the field, but also the tangled, turbulent components that filled the spaces between stars. Instruments like the European Pulsar Timing Array and Uneonograph in North America continue to expand these measurements, combining magnetic field mapping with searches for gravitational waves, cosmic rays, high-energy protons, and atomic nuclei arrive from every direction in the sky. Their paths are bent by magnetic fields, both within our galaxy and across intergalactic space. By studying their arrival directions, scientists can infer the large-scale structure of the magnetic skeleton. Facilities like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah track the cascades of particles cosmic rays produce when they strike Earth's atmosphere. Over time, these data can reveal the hidden deflections imposed by magnetic lines in the space between galaxies. Observation alone cannot reveal the past. To understand how today's magnetic fields came to be, scientists build simulations, mathematical models of plasma and magnetic fields evolving under the laws of physics. These simulations begin with different seed scenarios: primordial magnetism from inflation, fields injected by the first stars, or random turbulence, amplified over time. By running these models forward billions of years, researchers can see which scenarios match the structures we observe today. Such simulations require immense computing power, often running for months on supercomputers, and produce virtual universes that can be compared directly to telescope maps. One of the most promising strategies now emerging is to combine multiple datasets, polarization maps, galaxy surveys, CMB data, and cosmic ray measurements into a single framework by the location of galaxies, the shape of the cosmic web, and the patterns of magnetic fields. Scientists can test whether the skeleton is truly primordial or built later. If magnetic lines align with structures that could only have formed after galaxies, astrophysical origins gain support. If they extend beyond those boundaries, primordial origins become more likely. Despite these powerful tools, there are limits. Magnetic fields are defined relative to the vacuum. They have no surface, no boundary, and no light of their own. The further away they are, the harder they are to detect, and the weaker their signature becomes. To measure fields in the cosmic web's vast voids requires sensitivity to polarization changes so small they approach the edge of instrumental noise. To detect signatures in the CMB demands stability beyond anything yet achieved in space-based telescopes. These challenges mean that the quest to map the skeleton is slow, with progress measured in decades. But the potential payoff, understanding the oldest, most elusive structure in the universe, drives the work forward, in a sense. The tools themselves form a kind of human-made magnetic skeleton. Radio dishes spread across continents, linked by invisible lines of data. Satellites orbiting Earth, their instruments tuned to the faintest whispers of light. Particle detectors buried in ice or spread across deserts, waiting for a signal from the stars. Each is a node in a global network, a structure built by human hands to trace the structure the universe built for itself. The next chapter will step back from the instruments and return to reflection, to the philosophical weight of what it means for the universe to have an invisible skeleton. In the closing thoughts, the focus will shift from the technical to the timeless, how uncovering the magnetic web changes our understanding of what the cosmos is and our place within it. In the vast theater of the universe, it is easy to believe that what we see is all that exists. Stars flare and fade. Galaxies wheel in slow arcs. Light travels for billions of years to reach a watching eye. We have built our understanding of reality upon the visible, the luminous. Yet, the magnetic skeleton reminds us that the visible is not the whole, perhaps not even the most important part. Every spiral of a galaxy, every thread of the cosmic web, every drift of dust between stars moves in quiet dialogue with magnetic fields. They are not the headline acts of the cosmic drama. They are the stages, beams, and hidden scaffolding. Without them, the story might unfold in a different shape, or not at all. This realization forces a kind of humility. Humanity evolved with senses tuned to light, sound, and touch, but almost blind to magnetism. Only through the tools of science do we perceive the invisible tension that has been here all along, holding the sky in its lines. At first glance, the universe appears chaotic, stars exploding, galaxies colliding, black holes devouring matter in incandescent jets. Yet magnetic fields suggest an underlying order, an architecture laid down in patterns that persist across billions of years. If these fields are primordial, they are older than the first star, older than the first atom. They would be survivors of conditions when the universe was a hot, featureless plasma, a time before structure, before complexity. That such delicate patterns could endure from that chaos to now speaks to a hidden continuity in nature, a thread unbroken by time. Magnetism carries a duality. It is delicate enough to nudge dust grains into spirals within a star-forming cloud, yet strong enough to launch streams of plasma across millions of light-years. It is both the gentle hand shaping planets and the raw force behind cosmic violence. This mirrors the duality of the cosmos itself, creation and destruction, stability and change, order and entropy. To see the magnetic skeleton is to witness both sides at once, the quiet guidance of structure and the explosive release of stored energy. Understanding that an unseen framework underlies the universe alters how we view its history and its future. If magnetic fields influence the birth of galaxies, then the very arrangement of the night sky is, in part, their work. The constellations, patterns of stars that guided ancient sailors and storytellers may exist where they do because of magnetic lines drawn long before Earth formed. It also deepens the mystery of origins. If these fields arose in the first instant after the Big Bang, they may hold information about physical laws we have never observed directly. They may be silent witnesses to the birth of time, carrying within them a signature of forces that shaped everything that would come. There is something deeply human about searching for what cannot be seen. Ancient navigators followed stars beyond the horizon, trusting the invisible curve of the earth. Explorers crossed oceans believing in lands no map yet showed. The study of the magnetic skeleton is a continuation of that same instinct, the belief that the unknown holds meaning. In revealing the magnetic framework, we are reminded that reality is layered. The visible universe, with its stars and galaxies, may be only the surface. Beneath it lies the architecture of fields and forces, and beneath those may be deeper laws still, waiting for discovery. The skeleton of the sky is not fixed. Fields shift, twist, and reconnect. Galaxies will drift apart under the expansion of space, their magnetic threads stretching thinner until they snap. In the far future, the magnetic web may dissolve, its influence fading into the dark as the universe cools toward its end. And yet, even in that distant epoch, the imprint of magnetism will remain fossilized in the arrangement of the last structures, in the trajectories of the last particles. It will outlast the light of the last star, leaving its shape in the darkness. For all its vastness, the universe is not indifferent to structure. Magnetism demonstrates that complexity is not an accident but a feature written into the laws of physics. Without it, the paths of matter would be different, the story of galaxies would change, and perhaps life itself would never arise in this way. The magnetic skeleton is not just an astrophysical curiosity. It is part of the chain of cause and effect that led from the birth of the universe to the existence of conscious beings who can ask why it exists. In searching for the magnetic framework, we are also mapping the limits of our perception. The tools we have built, vast radio arrays, delicate satellites, deep space probes, are extensions of ourselves, designed to feel what we cannot feel, to see what we cannot see. Each discovery pushes back the boundary between ignorance and understanding, and with each step, we find that the universe is both stranger and more coherent than we imagined. Picture the camera drifting outward from Earth. The continents fade, the clouds dissolve, the moon slips away. The Milky Way's disk appears, its spiral arms dusted with stars. Then, faintly at first, a tracery of invisible lines begins to appear, arcs and loops stretching between stars, filaments connecting galaxies, threads lacing clusters into the great cosmic web. It is the skeleton of the sky, revealed not by light, but by the understanding we have built. It is delicate, ancient, and unyielding. It holds the shapes of all things, from the smallest grain of cosmic dust to the largest structure in the known universe. In the quiet darkness, where no light marks the way, the universe still holds its form. It is traced in the magnetic lines that have always been there, the silent skeleton of the sky, waiting for us to notice.